right, hello everybody, and welcome to our session, Building Global Scale Applications with Managed Databases and Cloud Runtimes. I'm Harish Jayakumar. I lead the Global Solutions team here at Google Cloud. And today, along with me, I have John, who's our product manager from the databases team, and then Sean as well, from a customer from Wayfair. We did plan to bring the piano and replicate something that you saw in the keynote today, but unfortunately, we couldn't fit it over here. And so you're not going to have the three of us sing. We're just going to have a talk over here. And I think I just realized that it's Sean and John. All right, cool. So our agenda is pretty simple here. We're going to start with defining what a modern application is. Then we're going to talk about how we're going to build a modern application using Google Cloud. And then we're going to have John, our customer, talk about the story on how do you build these applications and using it in Wayfair. And then we're going to open it up to Q&A, after which you get to take a survey and say how great we were. So if you have something good to say, take the survey. Otherwise, come talk to us outside. With that, let's get started. So let's start by defining what a modern app is. So if I'm looking at people over here, right, depending upon who I speak to, your definition of what a modern application is going to be different. If you're an end user, you care about, hey, is it seamless? Does it work on all my interfaces, whether it's my phone, my laptop, wherever I'm going to be using it? If you're a developer, you simply want to just focus on the business logic. If it works on my laptop, I want it to work in test, pre-prod, production, and it needs to be just work seamless out of it. If you're an IT and you care about, hey, how can I get it faster to production? How can I make sure I have a simple CI/CD pipeline? Can I push my code faster, make it much more agile? How can I ensure I have compliance, security? And if you have a hybrid environment or a multi-cloud environment, can I use my applications over there seamlessly across them? And then finally, if you're a business owner, what you care about is, hey, I care about monetization, can I launch new features, and can I build an ecosystem outside of it? And the nature and complexity of these applications have also changed. For example, the most four important things that I talk about if you're building an application today is scale, reliability, speed, and being data-driven. So let's talk about scale. You just started this application, you're two people in a garage, you have 1, 2 users, and tomorrow suddenly you're this next successful startup and you have 1 million users. You need to immediately be able to scale them. And then reliability. Today's business is always, always on. So how do I ensure I get the reliability, security, and continuous availability of these applications? And then speed. We want to quickly kick off a new feature, provide an agile mode so that your users can immediately get them. And then finally, modern applications are very, very data sensitive. So how do you store, retrieve, and deliver these experiences with these applications as well? Great. So when we're talking about these kinds of designing applications, cloud-native applications, it's far more dynamic. So today, when you're starting to build this, you're going to start building them using a microservices architecture, any cloud-native applications, because tomorrow, you want to just change one feature, one part of the code. You don't need to touch everything else. A microservice architecture enables you to just focus only on that area. And then you're going to run them on VMs. You want to package them and run them in a container model. And then when you're building these applications, you're not going to go on a waterfall model, take months to build the code, but you want to make sure you have a continuous delivery of these applications as well. And gone are the days of pre-provision. You don't set up something and just wait for a server to just like, okay, it's all done. But when you keep these demands, how do I scale on demand that I keep getting from my customers? And finally, you want to avoid failures. So the resiliency of these applications is also super important. So as technology enables these attributes, users are also beginning to expect them. So they expect their e-commerce application, for example, that John's going to come talk about, to be intelligent and up-to-date with inventory and recommendations. So honestly, this is not just a technical thing. This is just part of doing business today. So we defined what an application is. We talked about the characteristics that's important. Let's go build an application. So what do you need when you first start? First, you're going to pick your choice of code. I don't know, you can go all the way from C++, Java, or Go, Python, whatever you're going to do. And then you're going to take this code and you're going to package them in containers as microservices over here. So you see over here, you have my microservices like a product catalog, checkout, ads, recommendations. Then you want to store your data. So that's a stateless application. I store my data. I pick a database where I want to keep everything in it. I've packaged my applications, running them as microservices. Now I need a container orchestration. So I would choose something like Kubernetes. Obviously, I've listed Kubernetes over here, but you're welcome to go use Cloud Run, serverless models as well. And now you want to also connect and secure these applications. So you have a service mesh you're using outside of it. And then finally, you want to be able to manage the consumption and reuse them, so you have an API management. Now, I know I've oversimplified it over here. There's things that I'm not covering, like data operations, logging, monitoring, all those pieces, but you get the gist of it, that these are the major components that make up as you're going and starting to design the application. So we've defined the application, we built the application, now let's go run them. So we have two parts I'm going to talk about over here. First, very simply, on top is our managed runtime environments, starting with GKE. GKE is Google Kubernetes engine, based off open source Kubernetes, and for the highest scale, 15,000 nodes that you can go, and it can be used across multiple zones and multiple upgrades as well, and you can use that to build your developer platform as well. And second, Cloud Run, we've got a big shout out today in the keynote as well. I talked about you could go even build your platform on top of GKE. Cloud Run, that's your platform. That's a fully managed serverless platform that you can get up to speed and just start running and start writing code ASAP and get deployed on it. Here's the cool part. Once you've designed your application, put it in a container format, you don't need to decide if I'm going to put it on GKE or Cloud Run. The really, really great part is that once it's in a container format and you've standardized your application in container format, you could put it on GKE today. Tomorrow you may decide and you can just move it as is and move it into Cloud Run. That's the cool part over here. And that's, in fact, I would recommend, if you're starting something today, you don't want to manage your infrastructure at all, no ops at all, you would start with something like Cloud Run. Whereas if you've invested in the Kubernetes ecosystem and you love YAML and you've always written YAML and you've put your entire ecosystem around it, you would use something like GKE. And then we also have a feature in GKE called GKE Autopilot that not only manages your control plane, but also your data plane as well. And similarly, coming down to the databases side, if you see over here, on the leftmost, we have Cloud SQL, which is a fully managed relational database service for SQL Server, MySQL, and PostgreSQL. And on the rightmost side, you have Spanner. That's a Ferrari, right? It's Google battle-tested, mission-critical database that provides unlimited scale. So Spanner was actually built for our own workload. So we built this back in 2017 to run the Google's ad business. And if you saw today in the keynote, they also talked about how they migrated entire. So Gmail now also runs on Cloud Spanner. And then in between is AlloyDB. It's our most recent offering. I think it's about a year. And it sits between, it brings you the best of both Cloud SQL as well as Spanner. It's our newest PostgreSQL compatible relational database with broad Postgres SQL extension support. So we have the applications, we built it, we have our cloud runtimes, and we have our managed databases. So these are all the Lego blocks. Let's put them together to build three different types of application. No two applications are the same type. So we're going to build three separate types of app patterns you're going to see today, starting with internal corporate applications. Then we'll move to how would a mission-critical application look like, and then finally we'll stop with an elastic applications as well. So let's take the first pattern, a corporate internal application, right? So let's pick something like a corporate HR application. So now you know it's an internal application, so it's going to be inside your corporate VPN for security. You don't need to worry about too much about it. And then what are the next characteristics? Business critical versus mission critical. So what's the difference, right? Mission critical is, hey, if this application goes down for even like 1 microsecond or millisecond, I'm losing like billions of dollars on it. Internal application is more business critical. It's not mission critical. Yeah, it's going to be a little bit of an annoyance, but you can still get along with it. It's not as cost sensitive. You don't need to worry too much about, like, I need to have the latest bells and whistles associated with it. And the SLA may vary, depending upon, you could have multiple internal applications. So what is your SLA, whether it's going to be your payment internal application or was it an HR database? And then finally, you want to make sure you don't have less to no ops at all. I just want to just simply have the application to go. I don't want to manage my infrastructure at all. And then we'll talk about what build packs is, which is a really cool feature that I like on this. So if these are the characteristics, I take the Lego blocks that I talked about, how would I build such an architecture? So I would take the application, and because internal apps don't receive high volumes of traffic, they could benefit using a combination of Cloud Run and Cloud SQL. So I would have my application packaged in containers, run them in Cloud Run, and then I would have Cloud SQL as my managed database behind it. And then because this is going to be an internal, I would put them inside a virtual private cloud, and I would have an IAP or an identity-aware proxy that can authenticate the users. Now this is cool, right? The IAP is what we use inside called Beyond Corp. We don't use VPN inside Google, right? All our authentication, everything happens through Beyond Corp. That's the technology getting using IAP when you're able to authenticate it. So now your entire private VPC contains these internal resources and users and has a strict security boundary enforced at the network level as well. Now, I know this is, again, oversimplification about it, but you can see how clean and easily you can do that for an internal architecture. Now, let's talk about two customers who are actually using it. Let's start with SAP. So I told you I'll talk about build packs. So SAP is actually using Cloud Run. They're using our source-based deployment approach. What does that mean? What it means is now you built an application. You don't need to worry about taking a Docker file, writing a Docker file, packaging in containers, all that stuff. Build packs does it for you. So you can see the actual code over here. The build packs automatically detects the language from the source code. So it takes from the source code, packages it, and then you can actually run it straight out of the box. So it's build, ship, run right out of the box. And not only that, inside Google, a big part of our internal applications are running on GKE as well. And here's an external customer, Carrefour. So what they're using is they are basically a retail customer, and they're using both GKE and Cloud Run, and they wanted to provide a more reliable and high available service to the customers. So they are using Cloud Run for development of their e-commerce platform. They're using GKE for their mobile application, and both of them in the back end, they're using Cloud SQL. So now they built this new system, and with this system, they're able to do about 6x faster operating speed, and they have average about 40% on operational costs and eliminate downtime as well. So that's the end of pattern number 1. Next, I'd like to call Sean to continue with pattern 2, mission-critical applications. Sean?
Thanks, sir. Hey, everyone. My name is Sean. I'm a product manager at Google Cloud for databases. Happy to be here today. Thanks you for coming to the session this afternoon. I will go deeper into the second and third app patterns, some of the more heavy hitters, if you will. The second app pattern we want to talk about today is about mission-critical apps. And these applications are a bit more complex, both in terms of the requirements that are required, but also in terms of the way they're connected with the other systems. And if you look at the examples we have, a banking transaction app might be kind of a standard. The number of mission-critical apps are not as many as, for example, internal corporate apps, but they have more dependencies. They also have a lot more interconnected systems and also more APIs that are exposed. A lot of the mission-critical apps also have higher requirements in terms of scalability, in terms of availability, and also things like low latency. And so the amount of resources that are required to power these applications are a bit higher than the first application pattern. Another kind of characteristic of mission-critical apps is because these are often used to power the businesses, these are oftentimes used for data analytics as well. So if you have a lot of important data as part of your application, your business users are keen to use that data for analytics and also for AI and ML workloads. And so these applications are not just standalone, but they also connect to different workloads such as analytics, machine learning, both training and serving, and also some of the more recent GenAI workloads that you have seen today to be more grounded on your enterprise data. And I guess last but not least, they also require a lot of governance and compliance standards to meet those. And so you want to make sure that the services that are powering these type of applications meet those standards. A typical architecture could be something like this. If you have a mission-critical app, a lot of these applications are not single region bound. They are multi-region in nature, and so you would deploy services that can support multi-region applications. They also sometimes have different traffic, so if you have a load balancer up front, you can actually deploy and direct your traffic based on the proximity of your users for each of the data centers that we have. In the middle section, you'll see that we recommend using GKE, which is kind of our flagship product for the compute layer. And GKE, we will distribute based on your application workloads and wrap it around with service mesh to handle the GKE fleets. In terms of the database, we recommend using you can actually use multiple different databases, but for this workload, AlloyDB's newest features are really great because they offer both high performance, they also offer 4 nines of availability, but also one of the cool features of AlloyDB is that it offers built-in analytics and AI ML capabilities. And so compared to the standard Postgres, LODB is up to 4 times faster for transactional queries. It's up to 10 times faster, as announced yesterday, for vector queries for GenAI apps, and it's up to 100 times faster for analytical queries. So if you have a ad hoc real-time analytical workload, instead of building a separate data warehouse and all the data pipelines, you might be able to get away with just using LODB for those ad hoc real-time smallish analytical workloads with just LODB. So for mission-critical apps, just to summarize, you want to make sure that it's multi-regional, that it supports different services, and of course, different workloads like analytics and AI and ML are supported as part of those services. One example we like to share is Fluidify, which is a Canadian company for blockchain. They're running their blockchain workloads on top of AlloyDB, which supports more than 2 billion records. As they moved over from Amazon Aurora to AlloyDB, they were able to achieve 3 times faster performance, but at the same time, reduce costs by 60%. So you kind of see that, sometimes it's easy to kind of assume that the services across the vendors are sometimes similar, but depending on the workload and the characteristics and their needs, there's actually can be quite drastic differences between the different vendors. All right. And the last app pattern that I'd like to talk about is elastic apps. These are a little bit different than the first two in that they're not more in terms of the amount of apps out there. This is more about the characteristics of the app. If you think about apps like social media, the number of apps out there might not be a lot, but the actual number of users using per app can be substantial. And so elastic application is something that we characterize as consumer-facing, requires 5 nines of availability. It can't go down because your business and your customers expect that. They have to have super low latency. They have to have fast read and write performance on the database. And these apps have to be able to scale up and down even for unpredictable workloads. And so a lot of the services that are good for these types of applications are based on serverless architectures. Because sometimes, like on holidays or on sports events where you can't really predict who will win, and you just have to make sure that your services can scale up, serverless services are probably a good candidate for these type of applications. And sometimes these applications also require things like global consistency because your application have global users, and also oftentimes they also require things like end-to-end encryption because a lot of these applications are consumer-facing. You want to make sure that the data that they handle are secure. A sample architecture you can see here is if your application is global by nature, you might want to use a global load balancer up front to be able to redirect traffic. Sometimes you might want to use like a cache or a CDN if you're more content heavy. But on the middle layer, Cloud Run is a good option for these type of applications because of the nature that it's serverless. It will scale up as needed, but also it will scale down to 0 if you have no traffic, which results in saving a lot of cost. A lot of times, as developers, we make mistakes in over-provisioning, where we're kind of wasting resources, or we're under-provisioning and we have some downtime. And so a serverless service in this makes you make sure that you are good for both scenarios. In terms of the database, we recommend using Spanner because it has virtually unlimited scale. So if you have an app and suddenly becomes a unicorn, rest assured you are covered with Spanner. It also offers 5 nines of availability, and so it's kind of one of our services at the highest level of availability. A lot of our customers in both gaming and financial customers use Spanner for those workloads. ShareChat is a good example for that. They're a social media company in India, and they are able to move a lot of their workloads to SharePoint. ShareChat, serves hundreds of millions of users, and they also serve multiple types of unstructured data, like images and text and movies. And so, when their traffic increased by more than 500% in a number of days, Spanner was able to scale up without any change in the application code and meet those demands and graphics. As a result, ShareChat moved more than 100 tables over to Spanner. And like the example before, they were able to save cost by 30%. So to summarize, when to use what, if you look at kind of the chart here, if we just think about the compute layer and the database layer, for compute, there's really kind of 2 options. like Harish mentioned before, if you're just getting started, you don't know how successful your app will be, and you want to make sure you're not wasting too much resources, Cloud Run is a good place to start. It's serverless, it's fully managed, and it's really easy to get started in terms of getting your app up and running. And then later on, if your app requires more configurations, more knobs and controls, you can always move those containers to GKE to get the best of that. And then there's also an autopilot version of that if you want the fully managed version of GKE. On the database side, it looks like 5 options, but depending on your workload, it can be more easier to select. If you're thinking of a relational database, if you need ACID transactions, if you need strong consistency, for example, it's really kind of 3 options: Cloud SQL, AlloyDB, and Spanner. And I kind of like to think Cloud SQL is our easiest, fastest time to market, get started kind of database. It's probably the cheapest to get started with Cloud SQL as well. And it offers 100% compatibility with the open source engines like MySQL and Postgres. And then if you have SQL Server, you can also migrate from like to like with Cloud SQL. And then recently we announced Cloud SQL Enterprise Plus, which offers 4 nines of availability. So if you want to start quickly but also need a bit more performance and availability, there's a special Cloud SQL Enterprise Plus version that you can also take advantage of. Next is AlloyDB. It's our newest database that we launched about a year ago. And in the keynote, we've talked a bunch about how AlloyDB has all the new AI features. Not only is it kind of the cool database, but it has open source compatibility with Postgres, which is one of the most popular growing open source databases in the world today. And AlloyDB is 4 times faster in terms of transactional queries. It's up to 10 times faster for vector queries, and up to 100 times faster for analytical queries compared to standard Postgres. So if you have a Postgres workload, it's pretty much a no-brainer. You should get started with AlloyDB. It's one of our newest databases, and it's one of our most popular database engines. And then if you have kind of the big workloads, you may need unlimited scale. You might need 5 nines of availability. You want multi-master and multi-primary. And you want strong consistency. The only database in the world that can do all of those is Spanner. It's a very special database that powers most of Google applications like Gmail and YouTube and others. And it processes more than 2.75 billion requests per second, which is more than an order of magnitude of any of our competitors can do. So it's kind of a true flagship product for the most demanding workloads out there. Those 3 are the relational databases. If you have special needs for a NoSQL database, which is a good choice for if your workloads has requirements for very fast writes, for example, Bigtable is a key value wide column database, which is really specialized for those types of workloads. Things like IoT or things like building a very fast write-based workloads. Bigtable is great. And then if you are building a mobile application on the Firebase platform, Firestore is a great database that integrates as part of that. It's also a document database. So if your application is based on Java or JSON, a document store might be very easy to integrate as part of that. So those are kind of our options. Again, these are the building blocks. We just showed you 3 examples of what you can do, but there are many more, and there'll be a Q&A session at the end that we can help answer some of the questions that you may have. And just kind of to close out, there are customers in every industry for every workloads and every users that we've been happy to support. And a lot of these customers have been with us as we trust Google as their cloud. And personally, I think Google Cloud is probably the best place to run the data workloads, not only because of the AI technologies that we've innovated in part of, but because of the battle-tested nature of our services that have been powering global apps for a very long time. And so with that, I'd like to invite John on stage to share how Wayfair has gone with their modernization journey.
Thanks, Sean. Okay, got it right here. Okay. Hi, everybody. My name is John Keane. I'm a director of engineering at Wayfair. My team support a lot of the back-end services, central product catalog, pricing services, as well as supplier back-end configuration and integrations. On top of that, the data eng and ML eng environment for catalog and pricing, et cetera. So what I'm going to talk about today is a little bit about Wayfair's journey and through over the last, really over the last 12 months or so. But really what I want to make it clear is when we talk about this, Wayfair uses almost everything that Harish and Sean spoke about. We have a significant implementation of GKE. My services run from everything from 50 to 90K TPS, sub 10 milliseconds at peak, 4 nines to a 12 petabyte data set in GBQ and GBT. So we have a wide selection of Google products that we use. The partnerships that we have with Google are very deep, and they range everything from like security and compliance to analytics. I can't cover all that today, so what I'm going to be talking about is the things in blue. We're going to be talking about the transformation from getting off these large legacy monolith databases in SQL, MS SQL, and going through a microservice transition, as well as getting into single-purpose databases using AlloyDB, Cloud SQL, yada, yada, yada. But it's going to be mostly the blue boxes. So. It's going to be, we have about 10 minutes, well, a little bit longer than that, but about 10 minutes. And so it's going to be a high-level overview. If you have any questions, I'm happy to answer questions at the end. Can go deeper in any particular area, but we're going to stay pretty high level as we go through this. So what is the problem? And I think I'd be surprised if everyone in this room wasn't suffering a similar problem. You have architecture that, well-intended at the beginning, it grows organically over time, and pretty soon you kind of wake up one day and you're like, oh my God, what do we have here? We have to unwind this. We want to make progress. And what you find is that your ability to innovate is taking longer. And when you want to get to the new technology platform, to unwind some of the complicated knots of wires is difficult. In our case, we had widespread use of shared data. So we had, think large databases, order, product, customer, et cetera, large SQL server instances that many, many teams did direct reads and writes to. So unwinding that is a very difficult problem. And what we found is the more we built, the more complexity we introduced, and the more it took to maintain and innovate. And it slowed innovation. So, and the thing was that we found was obviously the cost to extend is not only an impact on compute, but also on people resources too. So you need more people to power more software, and the costs grow. And so how did we approach this? So as we think about it, the one thing, untangling those wires took a very concerted effort. The thing to understand is these databases will have tens and tens of thousands of database objects, so all being used by many teams across the company. And we realized through this process that, this is a 700-person organization with hundreds of atomic teams. And we realized through this process that we couldn't allow for teams to vary on their own and choose their own path. We didn't have a common way of describing process. One team would say they're 20%, hey, John, I'm 80% through my tech transformation. And another team would be 50% through. But they were talking about different things. One would be measuring just a portion of it and such. And then we didn't even have and because there are different common denominators, we couldn't actually determine progress. So if my boss or my boss's boss asked me how far we were through it, because we're setting capacity aside from our business stakeholders, we couldn't really give an answer. So we needed to create these buckets to allow us to then put metrics within each one, and teams could then describe where they were on the journey. And then also we could then measure it and talk about progress. One thing, the way we approached it was, first of all, we wanted to define ownership of all these key database objects. Again, 10,000 entities. We used algorithms, et cetera, to map these and assign ownership across our 4,000-person engineering organization. And then we brought in a federated graph from Apollo to help us create an abstraction layer between the clients that were asking for data and the data stores on the back end. Because in the end, our goal here is to get to these individual microservices and individual single-purpose databases, like Harish and Sean talked about, and be able to leverage those patterns that we talked about earlier. And finally, the last thing is we partner with Google and Apollo to actually help us train our staff, because one of the things we realized was although people had experience with Google Cloud and people had experience with Apollo Federated Graph, they didn't actually have the depth of knowledge that needed to make some of the most complicated decisions and to architect it for the future in the right way. So we partnered to bring in additional training for the teams. So the before and after architecture. So when we talk about moving from unwinding these wires, I'm going to talk about a single service, but keep in mind that every single one of these teams, we're talking about hundreds of teams, and each one has many, many services, all doing live reads and writes to these shared databases. What we found is no one team actually had autonomy because there's no clear ownership of data, right? Like, so if your service, and one example is our product database is getting 242 million direct select star from XYZ, direct reads against the database every single month. So if you are on the part data team and you want to unwind your parts of that table product, you can't do it because you have all this live traffic coming to it. There's no way that you can actually affect change. And then moreover, change is federated across the ecosystem. We have large scale replications of these databases throughout the entire ecosystem. So even if you have the contract that you know and you know the calls that are making directly on that instance of it, your replicated instances may be getting live traffic themselves, so your data contract's actually extended and throughout the entire organization, which makes it almost impossible to make any changes. So what we wanted to do, and so our goal was, again, to get to Cloud SQL Spanner, every team to be able to have autonomy within their data and their data domain. And so, the last thing is that even the services, where we had services in place, they actually mirrored the data structure underneath. So the same data contract that existed in the table, existed in the replicas, also manifested themselves in the request response services typically sitting on top. So what we did was we, as I mentioned, federated graph, and we brought in Apollo. And what we wanted to do was create a logical abstraction between the clients calling the data and the data sources and the services themselves. And that's federated GraphQL is actually excellent for that. It allows you to create a logical representation for the schema. And actually, it represented the first time in our history where we actually had a separation between the physical, how the data was stored at rest, organized, and how clients, storefront, our partner home UI, actually requested the data. And in this future state, they will not have to understand anything about the underlying service architecture, just understand the data that they actually need to consume. Let's see, what else? And so again, with these changes in this architecture, it allowed every team to own their own space of data and have a clear line of sight in how to improve it. They actually had a clear line of sight in how to improve their overall architecture and drive it. Now, this is one service. Again, we're talking about hundreds of atomic teams, 700-person organization, and scaling this across that large organization of people so that they're all making the right decision is the challenge that we're undergoing right now. We're some distance into the journey as is, and we have some wins and some losses through it. It's difficult to organize that many people and have everybody, because you have a lot of interdependencies. You know, some teams may use the same source of data, and how do you sequence those things? As we kind of go through it, that scale, that ability to do that in such a large amount of people, is actually where we're investing pretty heavily. And I mean, I guess I can't be at this event without talking about Gen AI in some way, some slide having Gen AI in it. But this is actually an area of significant investment for us, because we believe that this is the opportunity for us to radically accelerate our code migration and tech transformation journey. So here's the things that we're doing. again, we have tens of thousands of database objects. We have, by the way, we've had, as those database objects have aged, some people haven't maintained them in years, and the people who wrote them aren't no longer here. So we have to not only understand them to build a new schema, but then we also have to scale that out across an organization. So what we're doing is we've partnered with Google, Palm 2, Code Bison, et cetera, to, one, take embeddings, look at our corpus of knowledge, Wiki, Confluence, think that sort of thing. Use embeddings for that, and then use that to understand, with an LLM, to understand what the SQL code is actually saying. So if you have something SPID, well, how do we abbreviate SP? What does that mean in most colloquialisms when we use it? Okay, it means this sort of thing, or SU, supplier, So use embeddings to help build that corpus of knowledge and generate understanding and documentation for all those legacy SQL objects. It will also use that knowledge and understanding and training to then build the GraphQL schemas for us. And then Code Bison will also then be able to generate the code, the backing subgraph code on the back end, and connect up the Java, Python libraries to that GraphQL schema that it just built. Roll that out. We have systems to roll that out into production, do automatic PRs, do code checks, all that stuff, get that out. All of this at this stage is being wrapped by tests on both sides. And then the next step is to move the live traffic. That's going to be the tricky part, and we haven't started. We have this all kind of moving forward right now. We're in various stages of each one of these steps and getting it to production to be able to test on an isolated subset of the tables. But for the live traffic, what we'll do is we will actually have Cody, and we can prove we can do this. We'll generate a Python GraphQL query based upon the select statement. So select star or a select star with a join becomes a GraphQL query. We could push an automatic PR to the team that owns the code, and then say, here, you guys can own it, you guys can deploy it, use it, whatever, but you need to be off of it by this amount of time. And we believe through this process, it will radically accelerate our ability to get all of that live traffic, table product, 242 million things a month, get all of that off the database calls directly, and that gives the teams autonomy and space to own their own architecture and be able to get to AlloyDB, Spanner, like those SPDBs in the back end, and get us out of the legacy Microsoft SQL Server large-scale databases, which are expensive to maintain with the data file system and everything like that. Finally, the last bit is that step that I talked about at getting to the data store, which is using Cody and generative AI to actually help write all the migration scripts to go from the legacy table product to whatever you need. So for example, table product, 150 columns, may have, I don't know, 10 objects in it that are represented in GraphQL schemas. They become brand, or they become, maybe there's product, there could be part data. These are all entities within the GraphQL schema. We use that knowledge of what the system built and trained on to create those things for us. And then we use that to help build the migration scripts so that it will generate the migration scripts to move it from those 10 fields within table product to an AlloyDB or something like that, and then wrap it all with tests. So we hope, and I'm hoping I'm back here next year talking about the success of this, but it actually has the possibility to accelerate our tech transformation, help us with our customer stakeholders, because obviously, business won't sit and wait for 5 years for us to do this by hand. Two is it also allows us to get better tests and document our legacy code. I mean, those are two big wins. Even if we just did those, I mean, in some of these cases, it would be a huge win for us. So when we talk about generative AI, the interesting thing, I sat in a bunch of sessions yesterday, and one of the things a lot of times it seems to resonate is, we talk about like search and, image detection and image duplicate detection. Those are all, exceptional, image generation. But to me, this is one of the coolest things. I don't know if anybody has done these kind of things many times in your life, but having done this a couple times, you're working in the weeds the entire time, and something that can really help you document what you have, help you migrate to the new thing, is really exceptional, and the possibilities are endless for us in this space. Finally, the last thing I'll say is when we first moved into the cloud, I think everybody's been here, we ballooned our cloud spend. It went out of control. I mean, this is going to sound simple, silly simple, but what we did was we created transparency and accountability. We connected to the Google billing APIs. We put them in a spreadsheet, big visible spreadsheet. Everybody saw it. The spend got mapped to teams. And then we trained engineers on how to optimize it. Our goal was to get to 20% optimization. We actually were able to achieve 58% reduction in our spend annualized over a 7-month period. Happy to spend a bunch of time talking about that, but I just didn't think that any tech transformation, I shouldn't mention cost efficiency, because FinOps should be part of everyone's mindset in this room as they do cloud work, because the cloud doesn't allow for you to think of it over the wall like we used to way back in the day. Maybe I'm dating myself, but today it demands that every single engineer have understanding of both operational excellence, development excellence, as well as the cost and the financial component. Again, all of this wouldn't be possible. None of this would be possible without the great partnership, Kieran and our partnership with Google, helping bridge the gap with the product teams, as well as our black belt team that helped assist on some of the Postgres and SQL migration. I can't say enough about the Google partnership. It's really been instrumental to this, and that's part of the reason why I agreed to come here, and I'm really excited about this event.